Today what I'm going to do is walk you through a review of the topics that we learned in our polar graphing chapter. First of all, we talked about several different graphs, and I'm going to highlight some of the key ones. The first one is our rose graph, and I have two examples of rose graphs below. Things that we talked about was that the a value that is in front of the function, either cosine or sine, determines the size of the petal or the petal length. And then the n value in front of the n theta determines how many petals we will have. If n is odd, there are n petals. If n is even, then there are 2 n petals. Then the name of the function determines how the petal or how the rose looks. If it is a cosine graph, then our first petal is on the horizontal axis, like we see here on our left graph. If it is a sine rose, then the first petal is off of the axis. And to determine where the first petal is located, we are going to do n theta equal to 90 degrees, because sine of 90 is equal to 1, and that is the greatest value for the function. Now, to determine the rotation, we determine how much spacing is in between each petal. So we're going to do 360 degrees by the number of petals. Next up, we talked about our lemniscate. In our lemniscate graph, this kind of looks like what you guys often called an infinity sign. And the things that we need to remember is that the coefficient in front of the function is a squared. And since a is squared, we have to square root that value, and that will tell us the length of the petal. If we are dealing with our cosine lemniscate, then our first petal is on the horizontal axis. If it is a sine lemniscate, then our first petal is on the 45. And the petals are 45 degrees apart from each other. Our next set of graphs are the Limacon. The Limacon graph is either going to have an outer bump or an inner loop. And there are a couple features that we want to remember about our Limacon. First of all, just like with our other graphs, if it is a cosine Limacon, it'll be oriented with the horizontal axis, and if it is a sine Limacon, it'll be oriented with the vertical axis. The farthest point from our origin is going to be a plus b, and then the inner loop or the outer bump will be at the difference of a and b. If the difference of a and b is negative, then we end up having this inner loop. If it is positive, we end up having an outer bump. What I would recommend doing is just plugging in the quadrantal angles, 0, 90, 180, and 270, into the actual function to find the points that you will be plotting. The cardioid is a special case of the Limacon. In the cardioid graph, what we see is that the a value and b value are both the same. Because they are both the same, instead of seeing an inner loop or an outer bump, we actually end up seeing this point right at the origin at 0, 0. The distance that is the furthest from the origin will be 2a, and then the other points that are on the shorter axes will just be a units away from 0, 0. Again, just like the other graphs we've seen, if it is cosine, align with the horizontal axis, sine, align with the vertical axis. When we are doing our conversions between rectangular and polar form, there are a couple things we want to remember. In order for it to be in complete rectangular form, we can only see x's and y's, no thetas or trig functions. And to be completely in polar form, we can only see r's, thetas, or trig functions, no x's or y's. The conversions that we will use to switch back and forth are x equals r cosine theta, y equals r sine theta, and theta equals tan inverse of y to x. And the last one that we will use is x squared plus y squared equals r squared. Things that we want to remember, we want to make sure that when we are finding the angle theta, that we pick the correct quadrant based on the positive or negative of x and y. Now, things you'll want to review in your notes are how to convert points from rectangular to polar and vice versa, and also how to convert our equations. Things that we talked about when we were rewriting equations was we talked about that we can multiply or divide both sides by r. We said that we can square both sides. And we basically looked at how we could do direct substitutions, multiplying or dividing both sides by an r, or squaring both sides. And then once we got to a part where we could do a substitution of one of these formulas, then we would go ahead and do so. Review your notes from Chapter 9, the first unit, the polar unit, to see some more specific examples of that. Now, the big difference between real and complex, and this was something that was often confused. If we make a little chart here, we learned about rectangular and polar, real and complex numbers. Alright, so if we were dealing with real numbers, a real rectangular point would just be an ordered pair xy, and a real polar point would be a point r theta. If we are dealing with complex, which means it includes imaginaries, my rectangular coordinate would be x plus yi, or this is also commonly written as a plus bi. With polar numbers, we see this as r cis theta. And if you remember, r cis theta stands for r cosine theta plus I sine theta. It is the I that we see in the rectangular and polar form that makes a number complex. When doing basic arithmetic with imaginary numbers, we are going to treat the real numbers and the I numbers like terms. For example, if you were asked to FOIL 5 minus 3i times 2 minus 6i, you would FOIL just like we do with any other parentheses, giving you 10 minus 30i minus 6i plus 18i squared. Then at that point, you want to remember the powers of I. And we have I to the first, I to the second, I to the third, and I to the fourth. And the powers of I to the first is I squared is negative 1, I cubed is negative I, and I to the fourth is positive 1. So at that point, we see that I squared is equal to negative 1, and we're going to go ahead and do a substitution, turning this into negative 18. And after I combine like terms, negative 18 plus 10 gives me negative 8, and negative 30i minus 6i. Oh wait, hold on, that should be plus 6i, my mistake. Negative 30i plus 6i is going to give us minus 24i. Now when we're dealing with multiplication and division of complex numbers, we can either multiply and divide them the way that they see, or we can use de Moivre's theorem. And what de Moivre's theorem tells us is that when we multiply complex numbers, we are going to multiply the r's and add the angles. If we are dividing, we are going to divide the radius and subtract the angles. And this is only when those polar numbers are in r cis theta form. So for example, if we take a look at the example that we see here, I would do 4 times 7, which gives me 28, 30 plus 150, I'll have cis 180, and then depending upon the problem, it might ask me to give my answer in rectangular form. If that's the case, I'd multiply this back out, and that would be 28 cosine 180 plus 28i sine 180, and we know that cosine 180 is negative 1, so that gives me negative 28. Sine 180 is 0, therefore my answer is negative 28. Now in terms of my division problem that I see here, I would do 2 divided by 6, cis, and then I'm going to subtract those angles. In order to subtract them, I would need like terms. So if we rewrite them with denominators of 12, that would give me 15 pi twelfths minus 8 pi twelfths. So I'd be looking at 1/3 cis 7 pi twelfths. And since this answer is not on my unit circle, I would leave this one in my polar form. The last thing that we looked at was how to use the power rule for these complex numbers. And what our power rule says is that I would take if I have r cis theta raised to the nth power, I would do r to the nth power cis n times the angle. So in order to use that rule to help me solve this problem, I need to first put it into my r-cis theta form. And the way that I'm going to do that is 4 plus 4i. 4 is my x, the other 4 is my y, therefore my radius would be 4 squared plus 4 squared, and then square rooting it. So my r value is going to be 4 root 2. If we visualize the location of this angle, it would be right here. And that angle right there, where the 4 and the 4 are equal, would be 45 degrees or pi fourths. So this problem can be rewritten as 4 root 2 cis pi fourths raised to the 6th power. Now at this point I can go ahead and I can apply this theorem, which will be much quicker than doing 4 plus 4i to the 6th power by hand. So I'm first going to do 4 root 2 to the 6th power cis 6 times pi fourths. At this point I'll go ahead and simplify my 4 to the 6th power. I'll do root 2 to the 6th power, and that ends up giving me 32,768, and then this will be cis 3 pi halves. And again, if we are asked to split this out, cosine of 3 pi halves is 0, sine of 3 pi halves is -1, so I end up getting, we can just simplify this as negative 32,768i. And that's again because the cosine of the angle is 0, the sine of the angle is equal to -1, and then we also have that I in there. Alright, last up in our simplifying with imaginary numbers is de Moivre's theorem. And de Moivre's theorem is used to help us find all of the roots of a complex number or an equation. So the first thing that we need to do is we need to put our number, or put our value into r-cis theta form. After that, we are going to apply de Moivre's theorem, and de Moivre's theorem will give us the principal, or first, root. After we get the first root, then we are going to find the spacing to get the rest of the spacing around the circle. To get the spacing, we do 2 pi divided by n, where n represents the index of the root. So 2 pi divided by n is going to give us the spacing for the rest of the roots. Alright, let me show you what I mean by that. So if we look at our problem here, before we can even do it, we have to put it into r-cis theta form. Again, if we think about this, my x value is 4, my y value is -4 root 3. I would suggest drawing a picture here. So if I have a positive x and a negative y, that means that I'm going to be down here in 4th quadrant. Here's my 4, here's my -4 root 3, and hopefully we're recognizing this as our 30, 60, 90 triangle, with this being my 60-degree angle. Being that it's a 30, 60, 90 degree triangle, my hypotenuse will be double my short side, so my r is 8. We can also get that by doing Pythagorean theorem. My angle is going to be 60 degrees, which again we can get by special triangles or by doing tan inverse of -4 root 3 over 4. Anyway, once we get that that reference angle is 60, we can find that this overall angle for the problem is going to be 300. Therefore, what I'm looking at is 8 cis 300 raised to the 1/3 power. From here, I'm going to do de Moivre's theorem. And de Moivre's theorem is basically saying I'm going to do 8 to that exponent, so 8 to the 1/3, cis, and then I'm going to do 1/3 times 300, which gives me 100. And this right here is my first root. The number of roots that I have are equal to the root that I'm taking. So if I'm taking the 3rd root, which I am here, I'm going to have 3 solutions. If I was taking a 4th root, I would have 4 solutions. In order to get my spacing, I'm going to do 360 divided by 3, which gives me 120 degrees. So what that means is that these answers are going to be 120 degrees apart around the circle. So my first root and actually this 8 to the 1/3 can be simplified to 2. So my first root is 2 cis 100. My next root is 2 cis 220 by adding 120. And then my last root is 2 cis 320. And these would be the 3 roots of 4 minus 4 root 3I. We can also use this method to solve problems such as if I were to give you the equation x cubed equals 27, then we could write this as x equals 27 to the 1/3 power, and normally we would say there's only one answer. We would say that the answer is 3, but that is the principal root. If we want to find all roots, then we would rewrite 27 in r cis theta form, and then apply de Moivre's theorem, and then we could get all of the roots that we have. This would definitely be a good topic to go back and refresh on your notes.